Problem 156. Evaluate the integral of y cubed dx minus x cubed dy, where c is included in two circles of radius 2 and radius 1, centered at the origin, both with positive orientation. Now we're going to use Green's theorem here, but you might say, hold on a minute, we have a problem. Because I talked about in the last video about a simply connected region. Now what's going to happen here is we're just going to look at this region, not with a hole in it, but just kind of in a circular shape. And what I mean by that is if I go this way, there is my counterclockwise direction. Now what I'm going to do is I'm going to cut left here and go in and into this inner circle, come all the way around, and then come back out again. So what this does, it creates my region, and it's still in a counterclockwise direction because think, I went this way, I went that way, I went in, and I'm just going to do it on the one side there, and then I went down and around, and I came back around the other way, and then I went out. So if you think about all of those components there, I'm still in a counterclockwise direction, and it is a simply connected region because I went around the circle by using this slice here. And if you notice here, when I went in and then when I came back out again, it actually negated itself there. So it actually gives me that region completely, believe it or not. So that's my roundabout way of using Green's theorem when I do have a hole. So in a sense, I could do this with at least a finite number of holes. So that's the neat idea, and we can still use Green's theorem because of the way we look at this problem, not because of the way it is. So let's get started then. So first off, I want to determine which way I'm going to go with this. Am I going to use f dot dr or am I going to use qx minus py dA? And that's the way I'm going to go here because it's going to be easier for me to think about this area here than it is to find those RTs and do all that stuff there, because then I'll have to think of all of them here. This would be one RT all the way around here. That would be an RT going in. That would be an RT inside. And that would be an RT coming back out again. That's a lot of RTs, which means a lot of integrals. And if I think about it the other way, I can just do a double integral one area. Done. So I'm going to go with the one over here, which is the qx minus py dA. So first, we have to understand our vector field. So then our f is going to equal, now remember this first component here is my p dx. There's my p dx there. And that means my p is going to be y cubed. And then I have my q dy, and here's my q dy. So my q is going to be minus x cubed. So there's my vector field. Now I'm ready to roll with this one because I can set up my double integral now. Almost. So I have to find my qx. And that's my second one there. The partial derivative with respect to x is going to be negative 3x squared. And then I have my py here, and my py is going to be, and that's the p there with respect to y, so that's going to be 3y squared. Now I'm ready for my double integral. So let's write that out. So here's my double integral, and I'm just going to write d for now. I want to make sure everything's all set up before I plug the bounds in for this and how I'm going to actually evaluate this function. So I'm going to get my qx. So my qx is going to be negative 3x squared minus my py, that's here, and that's going to be minus 3y squared dA. Now I'm going to pull a negative 3 out of these two here. So that's going to be a negative 3, the double integral of d, x squared plus y squared dA. Now when I see this and I see these circles, I'm thinking polar all the way. So that's why I like to set that up last, because it determines which way I'm going to go too, which what I have for a function in here sometimes sways me one way or the other. So this is going to be nice and polar because x squared plus y squared equals r squared. And that's what I'm going to use here. So this is going to equal the double integral. And I'll talk about those bounds in a minute, which actually are very nice bounds, believe it or not. This is going to be r squared. And then if I'm turning this into polar, this dA, I need my Jacobian, which is r, dr, d theta. So let's talk about r now. R is going to run from 1 to 2. It can't be less than 1, so my r is going to be from 1 to 2. And my theta is going to go all the way around here. So it's going to be 0 to 2 pi. So there's our setup. Very nice, easy setup for this one here. And don't forget my -3. I almost did. So now we're ready to roll. So I have my -3 here. I make sure I put that first now. And this is really 0 to 2 pi. The integral from 1 to 2. R cubed dr d theta. So for my first r, or I should say for my first integral, dr, the integral from 0 to 2 pi, that's going to be 1/4 r to the 4th, and that's going to be from 1 to 2 d theta. Okay, so I get -3, the integral from 0 to 2 pi, and then I'm just going to pull the 1/4 out here, and then I'm going to do 2 to the 4th minus 1 to the 4th d theta, and that's going to equal, I'm just going to pull this all the way out now, so that's going to be -3/4, the integral from 0 to 2 pi, and inside of there, 2 to the 4th is 16 minus 1, so that's going to be 15. So 15 d theta. Now I can pull that 15 out too if I wanted to. I'm not going to worry about it now, but it's okay. That's just going to be a -45 on the outside, which I'll probably do once I get my answer here. So then this is going to equal really just theta when I integrate. So I'm going to write that out here now, -45/4. And I have theta here. And that theta is going to go from 0 to 2 pi. So then for my final answer, I have -45/4. And that's going to be from 2 pi and minus 0 there. So this is going to end up canceling with one of those there. So I get a 2 on the bottom here. So this is going to be -45 pi over 2. So there's our answer for this one. So there it is. That's our answer for this one. -45 pi over 2. And again, we can deal with the Green's theorem with holes as long as we look at the path in a different way.